Oh, hello, everybody. I'm very pleased to introduce Kevin Knudson from the University of Florida today. He's going to give a talk on discrete stratified Morse theory. So, Kevin, please, the floor is yours.
Okay, thanks, Neja. Um, Neja and I go way back. So actually, I got started in discrete Morse theory. It must have been 2004. Neja and I met at a workshop that Herbert Edelsbrunner and John Hara put together at the IMA in Minneapolis. And in fact, this figure here, this is a discrete Morse function on the torus. Uh, Actually appeared in the paper that we wrote, which appeared in Experimental Math back in 2005. So I've gotten a lot of use out of this image. Um, and so it's nice to be here to tell you about this stuff that I've been working on for the last couple of years. So this is joint work with Bei Wang at the University of Utah. In fact, I'm flying out there next week to talk more. Um, Here's a quick outline. So I'm going to remind you what discrete Morse theory is. I think most people know what's going on there, but I'll remind you. Then I'll tell you about how one might do this in a stratified way. I'll give you some algorithms, and then I'll talk about some theory related to this that we've sorted out. We don't have a complete story, but we've got a pretty good handle of what's going on. Most of what I'm talking about today will appear. The paper's been accepted to DCG, and it's appearing sometime, well, whenever these things appear. So we'll see. So let me remind you quickly about discrete Morse theory, just sort of set the stage and sort of how I want to, the notation I'll use and things like that. So remember, so in this talk, everything will be simplicial complexes. A lot of this can be done on regular cell complexes or even cell complexes that aren't regular. But so remember what a discrete Morse function is. It's just a function that assigns a number to each simplex. So we'll often just sort of abuse the notation and just say it's a map from the complex, but it's really the set of simplices that you should be thinking of here. A number is attached to each simplex, and it's not arbitrary. It has to satisfy a couple of conditions. So I'm introducing this notation just so when I do something later, you'll understand where it came from. So for every simplex, if you have a p simplex alpha, I've got two sets. I'm going to call U of alpha is the set of cofaces, so the p plus 1 simplices that contain alpha, where the function value goes down. There's a less than or equal to there, which often you just, you want to assume that your functions are injective, but they don't have to be. So less than or equal to, I'll call that the upset maybe. And then there's the lower set, L of alpha. That's the set of faces, codimension 1 faces of alpha, where the function value goes up. So it's a discrete Morse function just means generically that function values just increase as you go up in dimension generically, but you're allowed to go down at most once. So the condition is that these sets both have cardinality at most 1. And in fact, Foreman, this is due to Robin Foreman. This goes back to his paper in the late 90s. Foreman actually proved that these things are exclusive. In other words, if one of these sets is non-empty, the other one has to be empty. And if both sets are empty, we say that the cell is critical. Okay. And so the thing here is that regular simplices occur in pairs. So those are the cells that aren't critical. So it's regular means that it has a face or a coface with a higher or lower value respectively. That's what goes on. And then you visualize this by drawing arrows. So you draw an arrow from the p simplex to its coface beta, where the function value goes down. And then because of this condition on the sets, for any simplex, exactly one of the following is true. It's either the tail of an arrow, the head of an arrow, or neither. In the last case, those are the critical cells. Okay. So that's my quick introduction to discrete Morse theory. I hope it's familiar to most people here. It's become a very common tool in applied topology, in combinatorics. It's a really useful thing. So the question then is that Bei and I wanted to attack was, well, okay, there's smooth Morse theory. So the idea behind discrete Morse theory was, you have Morse functions on manifolds. Can you do this in a sort of combinatorial way? Can you mimic this on simplicial complexes or cell complexes more? And a lot of the theorems apply. So I mean, I didn't state them all here, but there are the standard sublevel set theorems, right? So in smooth Morse theory, you know that if you have a Morse function on a manifold, if you have an interval of values where you don't pass a critical value, then you don't change the topology of the sublevel set for that function, right? So in other words, in fact, it's even better than that. The higher sublevel set deformation retracts to the lower one. If you do pass a critical value, then you can describe explicitly what goes on. You attach a handle to the lower sublevel set, and you then change the topology. Okay. That's all true in the discrete case. You can prove that Foreman proved those theorems. Everything works out like you want it to. So the question that we were sort of interested in is, well, okay, not everything's a manifold. So what do you do in the stratified case? So just like every talk about Morse theory has to have the torus with the height function, that's the picture that everybody uses. This is the picture that everybody uses for stratified Morse theory. This is the working example that Goreski and McPherson used. That's my suggested reference for all this material. It's a book called Stratified Morse Theory that they wrote back in the 80s. So this space here, what you should think of, this is a torus that's been pinched. It's had a curve pinched to a point, and then had a membrane stretched across the whole. Okay, so here that's the pinch point, and then this membrane has been stretched across the whole. This is not a manifold, right? Everywhere along this sort of the boundary of this membrane in here, it's not a manifold. The neighborhoods don't look like Euclidean space. Same deal here at this point. At this point here, it's not a manifold. It's a pinch point. But you can stratify this space. So I'll describe what a stratification is in a minute, but what you should think of here is that you can decompose the space into pieces in such a way that each piece is a smooth manifold. So here's a stratification of this space. So this vertex, this one point, this pinch point, is a stratum by itself. And then the sort of boundary curve of this membrane, this one stratum like this, that's a one manifold. Now it's not a compact one manifold. If you add in this point, then it is. And then the two stratum, well, there's two two-dimensional pieces. There's this, the membrane that you got, and then also the torus. If you remove this pinch point plus this curve, now it's sort of a sheet. It's like a two-dimensional piece. You can see we've put some hash marks there. So this is how you stratify this space. And so then you might ask, can you do Morse theory on these gadgets? And so again, what do you think of here is you sort of have a height function on this guy. So say the height function just projects to a vertical axis in this direction. And where are things critical? Well, you still have your global minimum down here and your global maximum up here. Those are going to be critical. This point must be critical in some way. And then you might think, well, maybe here and here, if you didn't have that membrane there, they would be sort of critical points for the ordinary height function on the torus. And they are critical in this context as well. But the local topology is a lot different. So it's not the same thing as just attaching a handle like you do in the smooth case. It's much more complicated. And so just as an example here, what do the local neighborhoods look like? So around this pinch point, this local neighborhood is like sort of two cones, so this upper cone and lower cone, and then this piece of this membrane stretched across it. Okay, that's not just gluing on a handle. It's gluing on something else to this bottom thing. This point Y isn't critical for the height function, but you could imagine sliding it down here to the bottom. And the local neighborhood is like three sheets coming together, sort of like just three sheets coming together with a singular arc in the middle, like a Y-shaped sort of thing. This example will come up later. I'll talk about this a little bit more in the discrete setting. Okay, and so Goreski and McPherson, they have this very long argument. It takes like 75 pages to prove what goes on with this local data. So the question is, could we do this in the discrete setting? So let me begin by saying that our discrete stratified Morse theory is not the same thing as discrete Morse theory on stratified spaces. So it turns out, if you have these, so this is called a Whitney stratified space, and there's this technical condition that is not relevant for us here. But stratified spaces are triangulable. So Goreski proved that, and others did too, different versions of the same theorem, where if you have one of these Whitney stratified spaces, you can triangulate it in such a way that each stratum, when you close it up, is a subcomplex of the whole thing. So it's possible to triangulate these stratified spaces. Well, then you just have a simplicial complex. It's not a manifold, but so what? And you could imagine just doing discrete Morse theory on that, because that works on any simplicial complex. And that's fine, and I'll have some words about that later, but that's not what we're trying to do. What we want to do is do discrete Morse theory in a way that respects the stratification on a complex. So that's what we're going for. It's not the same thing as just doing discrete Morse theory on a stratified space. All right. So what's a stratified complex? So K will be my simplicial complex here. And what's a stratification? Well, it's a collection, a locally finite collection of disjoint locally closed subsets whose union is the whole thing. Now for us, all of our complexes are finite, so the locally finiteness business is redundant. But it can't just be that. You also have to satisfy this thing called the condition of the frontier, which says that if you take the frontier of each stratum, so close it up and throw away the interior, it's a union of lower dimensional strata. Or equivalently, one stratum hits the closure of the other if and only if it's contained in that closure. Okay, you can check that those two conditions are equivalent. Now for us, we're dealing with simplicial complexes. These strata will always just be a union of simplices, of the open simplices inside of the complex K. Right. Now here's a piece of notation we're going to use. So the set S here is the set of strata pieces. So we're going to use this fact that this gives us an assignment. S, which just says, okay, each simplex in K belongs to one of these stratum pieces. Okay, so that's how we'll sort of use strata like this. Okay. So what's a discrete stratified Morse function? Or maybe the funny story here is, I don't know if this should be discrete stratified Morse theory or stratified discrete Morse theory. In other words, what's the proper order of adjectives? But Bay started writing the paper in Overleaf, and she went with discrete stratified, and so this is where we are. I'm not sure it's right, but that's what we're going to go with. So, okay, so here's what we've got. So you remember these sets that I defined last time for a discrete Morse function a little while ago, U and L. Well, now we've got a complex and it's stratified. So we assume we have a stratified simplicial complex. And a function on it, F. Again, function meaning you attach a number to each simplex. And I've got these sets. So U sub S of alpha is, again, the set of codimension one, so the sort of the cofaces of alpha, the dimension one higher things, where the function value goes down, and you're in the same stratum. Okay, so you can imagine scenarios where you've got a P simplex, and then there's a P plus one simplex that it is a face of that's not inside the same stratum. That's entirely possible. So I want to look at what's going on inside the stratum containing alpha. Okay, so I have U sub S, and then I have L sub S is the same thing. It's the codimension one faces in the same stratum where the function value goes up. Okay, and so this function, again, this depends on the stratification, is a discrete stratified Morse function if for every simplex the cardinalities of both of these sets is at most one, and we have to throw in this third condition. If one is non-empty, then the other is empty. This third condition didn't come up in ordinary discrete Morse theory because you could, again, form and prove that if one of those sets was empty, if one of the sets U or L was non-empty, then the other one had to be empty. That need not be true. It relies on there being enough faces around. It really does rely on things being a simplicial complex. And these strata pieces are just sets of simplices. They need not be subcomplexes. It might be the case that you're missing some faces of a simplex, and then that proof that Foreman used just doesn't go through. So you have to make this third condition part of it. But again, it's not especially restrictive. You just have to have it there. And then a simplex is critical if both of these sets are empty. Okay. So in other words, it's not. If you try to leave going up, the function value goes up, and if you try to go down a dimension, the function value goes down inside that stratum. Okay. So in other words, another way to think of this is that the function is a discrete stratified Morse function if, when you restrict it to each stratum, it's a discrete Morse function on those strata pieces. Okay, that's really what this is saying. But then we have to throw this other third condition in to make sure that things are okay. All right. Now, this idea here of violators is really important. So if you write down an arbitrary function on a simplicial complex, it's probably not a discrete Morse function. But the question is, how can it fail to be one? So we call a simplex a violator if of these conditions associated with being a discrete Morse function, if one of these conditions holds. So this is not, there's no stratification here. This is just in general. If u of alpha, remember those are the cofaces of alpha where the function value goes down. So if there are two or more of those, that's a problem, right? You've violated that condition. Or if you have two codimension 1 faces of alpha where the function value goes up, two or more of those, that's a problem. Or it's possible that you could have both of these sets being non-empty. That's a problem as well. Okay, and these conditions need not be exclusive, by the way. You can have, you can have more than one of these conditions being satisfied at the same time. So here I've given you an example. So on the left is just a function, it's just a height function basically on this circle. And it's not a discrete Morse function. There's a couple of problems. There's two violators. This edge labeled with a 0, well, it has two faces where the function value goes up. That's not allowed. You're allowed one, but you're not allowed two. So 0, this edge is a violator. And this vertex 9 is also a violator because it has two cofaces where the function value goes down. Okay? So here, this is not a discrete Morse function. On the right, what I've done is I've stratified this space. And so I've got all the various pieces. There's 5 pieces here. 1, 2, 3, 4, 5, 6 pieces, sorry. And now this is a discrete Morse function, a discrete stratified Morse function with respect to this stratification. Okay, so now I've just made this edge 0 its own stratum. Okay, it's non-compact, but that's fine. These two vertices, 1 and 3, are now just strata by themselves. 9 is its own stratum. And then I have these two other strata pieces here. And I've drawn the discrete gradient on these two pieces out here. So 7 and 8 are both critical edges. I just didn't, they're not paired, so I just left them. I didn't color them red, but you might think of them as being critical. Okay, so violators are really kind of what makes things not a discrete Morse function. So maybe I'll pause there. Are there any questions before I move on? No?
Well, perhaps a very small one. So the idea is not to change too much. So you can just take an arbitrary one and sort of fix it, like in this case.
That's what the algorithm's going to be. Yeah.
Oh, sorry.
Yeah. No, that's great. You're going where I'm going. So right. So the question is, so you've got a function and it's not a discrete Morse function. Can you stratify your complex to turn it into a stratified one? Okay. So that's actually exactly what's coming next. So here it is. So suppose you have some function on your complex. This algorithm will spit out a stratification for which the function you started with is a discrete stratified Morse function. Now, in the worst case, I guess it could be, haven't run into one, it's possible that the stratification becomes completely trivial, like every simplex is its own stratum piece. I mean, in which case, you didn't help yourself very much. But here's how it goes. So you start with a function, and you look for all the violators. So we'll order them by increasing dimensions. So all the vertices come first, and then all the edges, and then all the two simplices, and so on. And then, okay, fine, so you've got a bunch of vertices maybe. Then you order them by function value, increasing function value. What if there's a tie? I don't know, pick one. It doesn't matter. Often we assume that functions are injective. You can wiggle them a little bit without changing much to to assume they're injective if you like. Okay. So that's the starting point. So you initialize your strata set to be empty, and then you just go through the violators one at a time. So take the first violator, toss it out of the complex, okay, and then consider what you've got by removing, let's say, the first violator from K. Now, one of two things happens. Either your function now has become a discrete Morse function, or it hasn't. Okay. If it has, well, then I've already thrown, sigma I, so say sigma 1, into the stratum. And now if, say, K throw away that first simplex was a discrete Morse function, well, now I have to create more strata. Now, the thing is, your complex throw away the violators that you've gotten through so far might not satisfy the condition of the frontier. Okay, so we always have to make sure that happens. So we add the following two strata. We take the frontier, which is you close up Ki, and then you throw away its interior plus those violators that live inside of the closure. Okay, and then you add the interior. Now, algorithmically, how do you do this? Well, you're trying to get your computer to do this. There's the old general topology trick of what is the how do you get the interior? It is the complement of the closure of the complement, right? And you can program your computer to do that pretty easily. Okay, so these are the two strata you add plus the violators that you've taken out up until then. If it's not a discrete Morse function when you restrict it to this complex Ki, well, then one of the sigma j's that's past your sigma I is still a violator. Others might not be. Sometimes when you remove a violator, other violators are no longer violators. Kind of interesting. So you remove the ones that aren't violators anymore, and then you just keep iterating this. And it's a finite process, so it has to stop. And then you can check, so theorem, this works, okay? It shouldn't be too hard to believe that this algorithm actually does generate a stratification that and the function you started with is a discrete stratified Morse function on it. There are sort of questions about uniqueness. Is this the only way to do this? Certainly not. If you order the violators in a different way, you might get a different stratification. Is one better than the other? There's certain, maybe I'll come back to that later. But it's not unique, but this does work. So here's an example. So here's sort of a split octagon. Topologically, this is a wedge of two circles, right? So here on the left, we just got an arbitrary function on this thing. It's not a discrete Morse function. But there aren't a whole lot of violators. 30 is a violator right here. And 31 is a violator. But that's it. And so so the algorithm would first remove vertex 30, and then you check, well, the restriction is still not a discrete Morse function because 31 is still a problem. So you move on to the next one. You remove 31, and now it does work. You can see the green arrows represent the gradient in each piece. If it's blue, it's critical. These edges become critical when you do this. They're not paired. And you have this gradient like this. And then you stop because those were the only two violators in the first place. And then, now, of course, topologically, what do you want to do? What do you want to use discrete Morse theory for? Well, you want to use your gradient to do elementary collapses. And so you can see you can collapse these pairs away, and you end up with this one edge 9, this one edge 19, and this one edge 32, which are sort of the three essential pieces. Everything else can be collapsed away up to homotopy, and then you still have your two critical vertices. And so topologically, you see that we've simplified the complex quite a bit. This is one of our main goals for doing this, is to simplify stratum by stratum. So this is a pretty simple example. Here's a slightly uglier example. So this is a tetrahedron, and I've exploded the drawing to make it easier to see everything. So on the left, I've got the one skeleton. and I've labeled all the edges and vertices. This is really just like a height function on this thing. And then I've got the two triangles, so 6 and 9. So 6 is this triangle and 9 is this one. Okay. And then 13 is the back face and 5 is the bottom face. Okay. This is very much not a discrete Morse function. There are a lot of violators here. So vertex 14 is a violator, for example. So is vertex 10. The other two vertices are okay. Then there's some edges and faces that are violators. So when you run this algorithm,
sorry, Kevin, just a minute.
Yeah.
There's a question in the chat.
Okay.
So I suggest that you just ask the question yourself, Arturo. Is that possible? Can you do it? Or I can read it out.
Yes, for sure. Sorry for interrupting again, but then what you obtain in a simplification is taking into consideration the function. So if you would have considered a different f, then your simplification would be something different or something like inherent of the shape of the graph.
I see. Yeah. So no. So the simplification is just topological. We just left those numbers on there to sort of label which edges they sort of came from. Because so in here, so again with discrete Morse theory, what do? You perform elementary collapses where you if you have a pair, you just get rid of them essentially, right?
Okay.
So yeah, we just kept these labels on here so you would see which things didn't get collapsed away. I wouldn't think of these function values as having anything to do with what happens after you simplify.
But it does have to do with how much do you simplify it. So for instance, if you would have taken another, so it is not going to change the topology, but maybe it will change somehow the representation because the collapse you're doing. So you're having a function in some way. The way I see it is you have a function and then you run this algorithm and obtain something that seems simpler at least because you collapse stuff out. So it could have happened that you get in the middle between A and C, and you get only something with a different F. You get something like less simplified. All right, thank you.
Yes, absolutely. Yeah. So right. So yeah, this function. Yeah, maybe there'd be other critical things with a different function. That's entirely possible. Yeah, that's right. But yeah, we all agree that topologically these three things are the same, right? So yeah. Okay. Good question. Yeah, it does very much depend on the function how much you can simplify. That's true. So for this tetrahedron, you run the algorithm. I mean, I won't, show you all the details. It just this is how I spend a lot of my time. I like pencil and paper algorithming. Just doing the algorithms and see what happens. So the algorithm that Neja and I developed with Henry King all those years ago to go from point data. I mean, I've sat in coffee shops and like manually done these things. So here, I told you that 14 and 10 were they were violator vertices, so you have to throw those out. And then once you do, you still don't have a discrete Morse function because there are other issues. You end up with this piece, this one stratum piece. So these two edges end up being critical because they're not paired with anything, and then this vertex 3 gets paired with this edge 2. I dropped the label. And then you have two two-dimensional pieces. So this simplex 6 becomes its own stratum piece. And then you have this other piece, which is topologically a punctured disk. It's three faces and three two simplices, and then you've this vertex 0, this vertex 10 isn't there, so it's like a punctured disk. Okay, and then I've shown the gradient on here. So the back face 13 remains critical, but this edge 7 gets paired with the bottom face 5, 4 stays critical, and so on. Okay. So yeah, another example of the algorithm. We have complexity bounds on this. It's not terrible. It runs pretty quickly, actually. And in fact, there's a visualization tool. So let me stop sharing this and let me share something else. Here we go. So one of Bayes' students actually coded this up. So here I've got sort of a two-dimensional complex. There's no triangle in there. This has some random function values in it. You can just generate other random function values if you want, just to play with this. So, so the first thing I might do would be to mark the violators. So here I've got 3 vertex violators and 1 two-simplex. It's a problem. Okay. You can mark the critical simplices. They're in yellow. The non-critical ones are in green. And then show the stratification. There's lots of stratum pieces. Okay. And then you can start removing pairs. So, okay, there are no edge face pairs to remove, so fine. But I mean, I've got pairs here, so clearly I can remove that one. I can remove that one. And now, but see, I created a new pairing when I did this, when I removed that one, so I can remove that guy. And now I've got another pairing, that pairs. Okay, and now I should be done. I can't do anything there. So that's pretty good. And then, there are we have other columns. So here's here's a 2 complex, and I can random values on it or whatever. Let's mark the violators. Quite a few violators here. Criticals, non-criticals. But there's some collapses here. I can do this. I can show the stratification. A lot of strata. But let's start removing pairs. Taking stuff out. There's no more of those. Edges. Nothing more to do. And so now I'm done. Okay, so I've simplified this space to some extent. Okay. You can, the links in the slides, I'll put it back here. It's fun to play with. Okay. All right, so some theory about all of this. So if you have a discrete Morse function, is it a discrete stratified Morse function? Well, sure. In fact, any stratification, with respect to any stratification, a discrete Morse function is a discrete stratified Morse function. So that's reassuring. But you can go the other way too. So suppose I have a discrete stratified Morse function with respect to some stratification S. So on each stratum piece, xi, I look at the discrete gradient. So again, we've got these pairings of simplices. I'm not going to worry about the function. Got the discrete gradient on each piece. And I just take the union of those. That turns out to be a discrete gradient on the entire space. Not too hard to see. Reason being, because the pairings all take place inside of strata, you're never going to leave a stratum with a V path. So if you start looking at gradient paths, they stay inside strata. They don't leave them. And since there aren't any loops inside of any given stratum, you don't have any loops globally. Now, it's not the gradient of the function f, unless you happen to have started with a discrete Morse function in the trivial stratification, where it's the whole space. So it is a discrete gradient, but it's really not got much to do with the function f. So you might ask, can you choose a discrete Morse function that's close to f that gives you this gradient? I mean, you can certainly choose a discrete Morse function whose gradient is this. That's not hard to see at all. I mean, you hand me a gradient, there are infinitely many functions that are attached to it. Here's one thing we can say though. So here's a theorem about this. If I have a discrete stratified Morse function and I take the induced gradient vector field that I get by taking the union of the fields on all these pieces, let's assume we have a linear order on our strata. You can always do that. Then you can actually find a discrete Morse function whose gradient is v, no problem. But there are some numbers where the sublevel set for this discrete gradient, for this function g, discrete Morse function g, are the union of the strata up to that level. So if I pull back the number ai, the sublevel set at ai, it's the union of all the strata sj where j is less than or equal to I. So we say that such a function separates the strata. So one thing you should notice here is that, we're losing a lot of continuity by doing such a thing. And this should have already, maybe it wasn't obvious, but if you think about it for a second, there's really no relationship between the function values in a stratum and those in strata adjacent to it. And this makes this very stark. In other words, you can have function values being very small, say in a one stratum, and then when you go to the two stratum adjacent to it, the function values might be enormous. And there's no restriction on that. There's nothing in the definition that causes any problem there. So I'll have more to say about that later, but there's no relationship between the function values as you move from strata. So that's sort of like there's not really any kind of sense of continuity here. Not that you would expect. It doesn't even mimic continuity. That's what I would say. So what about the classical theorems? I mean, what we really want are sublevel set theorems. So in Morse theory and stratified Morse theory, there are theorems that tell you what happens when you look at sublevel sets for your function. Does the topology change when you pass critical values? What happens if you're not going past a critical value, and so on? We can say a few things here. We call them weak theorems because they are. Given a discrete stratified Morse function, if you collapse a non-critical pair, so you're only pairing things up inside of strata anyway, so that's a stratum preserving homotopy equivalence. So regular things don't affect the topology. You collapse them away. As a corollary, this is sort of a weak theorem B, we call it. If you have such a function, and you let V be this sort of union gradient vector field that I described earlier, then your complex has the homotopy type of a CW complex with one cell for each critical cell of V. Now this is just sort of standard discrete Morse theory. You've generated this thing. But your critical cells came about from the stratification, from the stratified thing. We don't have a theorem yet on sublevel sets. I'll say more about that later. So here's another theorem. What can we say about, well, okay. So suppose Z is some compact set and it's stratified. Suppose I have a stratified Morse function. Okay. So one question you might ask is, can you discretize? Is there some reasonable way to, given a it's not smooth, but a stratified Morse function on a set, can you find a discrete stratified Morse function that behaves the same way in the sense that it has the same numbers of critical points and things like that? So suppose I have a stratified Morse function on Z. So D will be the top dimension, Di is the dimension of the ith stratum. So here, so Ci is the Morse vector of F restricted to Si. So what's a stratified Morse function? Really what you've got is you've got your set Z, your Whitney stratified set Z. You always assume it's living in some Euclidean space, and that you've got a function a smooth function on the ambient thing, then you restrict it to this guy, okay? And the way it works is when you restrict it to each stratum, it's a Morse function on that stratum. That's what a stratified Morse function is. Suppose I have one of these things. So when I restrict it to each stratum piece, it's a Morse function, so it's got a Morse vector. This means that there are this many Ci0 critical vertices, and there's Ci1 critical points of index 0, and then index 1, and finally of index Di, where the index is given by the number of negative eigenvalues of the Hessian, right? Now, Goreski proved that you can triangulate Z so that each closed stratum is a subcomplex. So so I close up Si, it's a subcomplex that I'll call Ti. Okay, so this is how you do this. So here's the theorem. This is built on top of a theorem of Bruno Benedetti. So you can subdivide this triangulation R times, and R might be large. You might have to do this a lot. But once you do it, you can put a discrete stratified Morse function, capital F, satisfying the following. So the stratification is given by the various tk minus 1s. But and the restriction of F to the I stratum has discrete Morse vector. Well, it's not Ci, it's the dual vector. Okay, so in other words, I have to reverse the the dimensions like this. It's sort of a duality result. Okay, so so the answer is yes, there is a discrete stratified Morse function that behaves in some way like your stratified Morse function on the stratified set. Another question you might ask is, so suppose I've got a function on the vertices, so can we extend it to a discrete stratified Morse function on the whole thing? So this is analogous to the question that Neja and I solved with Henry King so many years ago now, where you start with a function on the vertices of a simplicial complex. Can you extend it to a discrete Morse function? We gave an algorithm for that. So the question now is, if I've got a stratified one, can I do it in a stratified way? The answer is sure. So our algorithm can be extended to this setting. You basically generate it on each stratum. That algorithm still works. You have to be a little careful around the boundaries. In fact, it leaves a lot of things critical. It's not an especially minimal sort of algorithm. You might get a lot of critical stuff. And really, that algorithm does generate a discrete gradient. So you get a discrete gradient on each stratum, but then you get a discrete gradient on the whole complex. So, and you can actually choose an extension that is a discrete Morse function, but it separates the strata. So let me just sort of illustrate this with an example. So I said the three sheets would happen again. So what you should think here is that this blue curve running through the middle is the one stratum going around that membrane in the torus. And then this is sort of the interior membrane. And then you have the two pieces of the torus branching away. You can't really see the back face very much. There's one part of it. So you've got three sheets coming together, like a Y shape if you were sort of to linearize it out a little bit. And I've put some values on the vertices, and then just run the algorithm. And so here on the one stratum, you sort of get this gradient flowing down to this critical vertex at the bottom, which is kind of what you would expect. But then on these sheets, you end up with a lot more critical stuff. So if it's red, it's critical. It's what the algorithm leaves critical. So it almost, in this case, what you would begin to think is maybe it's really sort of like creating almost like a tubular neighborhood of the one stratum would be left critical by doing this algorithm. So that's a first pass. You could certainly pair more stuff up. I mean, all these things are critical, but there's no reason I couldn't do a lot more pairing inside of here to get rid of a lot of critical cells. But we haven't studied that in any serious detail yet. So what are our long-term goals? Well, we want sublevel set theorems. Again, by that I mean, what happens when you go past a regular value? Does anything change? There we sort of see that nothing changes. But what happens? What's the local structure around critical cells? That's what we want to know. In the classical stratified Morse theory case, Goreski and McPherson proved that if you have a critical point for a stratified Morse function, the local topology decomposes as a product of two pieces. One they call the tangential Morse data, and one called the normal Morse data. So the tangential Morse data, what you should think of is, well, your critical point lives in some stratum, and you've just got a Morse function on that stratum. So you know what happens inside that stratum just from ordinary Morse theory. You glue on a cell of a certain index. But then you've got the normal direction. So that's when you're trying to go transverse to your stratum into other strata. That we haven't figured out yet. The smooth, I'll just call it smooth, the classical case really involves, you need something called the normal slice, which means that you've embedded your stratified space in some Euclidean space, and we're really trying to avoid all of that. And one way around it is to think about the lower link of what's going on around a critical cell. So, and I mentioned this before, I mean, if you have an arbitrary discrete stratified Morse function, the function values might just vary wildly from one stratum to the next. I mean, even if you have, an edge in one stratum and then it's got a triangle adjacent to it, that triangle might have its function value maybe nowhere near the one you have. So to get sublevel set theorems, we're going to have to insist on a couple of conditions. one is sort of a separation condition where the critical cells aren't clumped together. That's not too, you can subdivide to make that happen. But you want something like continuity, where if you take the closed star of a critical cell and you throw away the closed star inside the cell's stratum, those cells should sort of either be always bigger or smaller than where you are. And again, let's sort of illustrate this again. Here's 3 sheets again, where now I've put function values all over the place, like on everything. So again, here's this one stratum cutting through here. The lower link, remember, that's where you've got the function values are in the link, so remember the link is sort of the boundary of a simplicial neighborhood. So the lower link, at least part of it, there'd be another part on the sheet behind it, is here in this sort of royal blue color. We're just trying to understand the topology of these sublevel sets, and it's got to have something to do with the lower links. Goreski and McPherson have sort of, up to homotopy, they can tell you that it involves something about the lower links of the function. So we're still just trying to sort all this out. We don't have a good answer yet. Still work in progress. But something's got to be true. And we think something like the classical thing should be true, but we're just not there yet. So some other long-term goals. We want to use this for simplification. Can we use this to simplify complexes so that make computing Betty numbers easier, for example? Can we use this to help parallelize computation of persistent homology? Now, there are parallelized algorithms for computing persistence out there. What we mean here is that we want to do it with respect to the stratification, and then can we glue it together later? Just data analysis. Often data is sort of stratified. It comes to some sort of natural stratifications. Can we use this to help there? Bei has some ideas about visualization. That's she's really a computer scientist, so that's her department. But I always like to mention it. Then finally, we're working on a multi-dimensional version. So Fanfei is one of Bei's students, and Claudia Landy has joined on at this stage as well. Claudia and another group of people have worked on multi-dimensional discrete Morse theory. We're trying to do a stratified version. So the idea there is now your function is not just into the reals, it's into say a k-dimensional Euclidean space. And you can talk about discrete Morse theory in that case. Do you get interesting stuff there? So this is the last thing that I expect Bei and I'll be talking about this a bunch next week. I was just working out examples yesterday. So that is the end of my talk, and I've learned that nobody ever minds if you finish 10 minutes early, so I will stop there and be happy to answer any questions.
Well, thanks very much, Kevin. It was really, really nice, and so I would ask everybody for questions, please.
I've got the chat open now. Oh, thanks, Radmila.
Okay, yeah. So there's a chat. Just Radmila said thanks for a great talk.
Yep, got that open.
So while people are thinking about questions, I have a few.
Okay.
Okay. So you mentioned this along the way, but anyway, I'd like to ask you, when you're talking about this stratified discrete, in the algorithm that we put together many years ago, one of the components was that along the way you would do a lot of canceling of critical pairs, and that way you would simplify your discrete Morse functions, make it better for the purpose of the various purposes that you want to use it for. So
Yep.
do you do that in the I didn't notice that you would talk about that in the stratified case too. You said that you get a lot of critical simplices, but do you use cancellation to get rid of them, or is there any obstacle to doing that?
Yeah. No, there's no obstacle. So this is just sort of the nice. So this remember we have two parts. There's extract raw, and then there's the canceling thing. This is sort of the result of the raw algorithm. But what you'll notice here though that what are you going to cancel here? There's no paths to cancel. So I think really what needs to happen in this case is we need to figure out some mechanism for just doing further pairing inside of these critical bands that happen around the strata. Yeah.
has like really short paths, right? But you know,
They're
they
very
don't give
short
it to
paths,
them
yeah.
because they're too short. Yes,
There's
so
nothing to turn
you
around.
do you do that in the end, I guess, right?
Yeah, yeah.
Okay, okay. Any more questions from other people? Or I continue with my list. No, it's not so long, so you know. So the other question I was going to ask is, you talked about, you know, if you order the violators in a different way,
Hmm.
you come up with a different result. So maybe it can be better or worse. So you said that you would mention this problem
Yeah.
of optimizing the this ordering and the final results of your algorithm. So
Yeah.
what about
So,
it?
so what I'll say there is, okay, so um, okay, so you start with a function, and then the algorithm builds a stratification for which that function becomes a discrete stratified Morse function. That the result of that is not unique. Because it does depend on, you could choose a different order for the violators, and then you might possibly get a different stratification. So here's what we can say. Consider the set of all such stratifications for which that function is a discrete stratified Morse function. That's a partially ordered set. You can order it by inclusion. You say that one stratification is less than another if every piece of the one stratification is inside of a piece of the other one. So you get this partially ordered set. So what are the maximal elements in this are sort of the smallest filtrations. Okay. In other words, you know, being lower down in that post set means that you've got more stratum pieces, and so the algorithm generates a maximal element of that partially ordered set. But there might be incomparable maximal elements. So, I mean, I didn't include a picture, but this tetrahedron example, yeah, this one. If instead of throwing out vertex 10, I say first throw out vertex 14, but then throw out edge 7, say, okay, you get a different stratification. And it has the same number of pieces, but it's different. So as to whether there's no real reason to believe that one might be better than another, but you can get different stratifications for which.
So like proceeding by dimension doesn't really, it's not what you do, it's not something which gives you better results. Proceeding by, you know, starting with violators, vertices, and so on.
Well, that's it. Yeah, I mean, the algorithm does start with vertices and then go to one simplices and so on. There's no reason to do that necessarily. Like, there's no guarantee that is the optimal way to go. It's just sort of the logical way to go. I don't know.
But it does give you a maximal element in your partial ordering of the.
Yes, it does. It does. Yeah. Yeah.
Okay. Well, do we have any more questions?
Well, I might just ask one, maybe repeat the one that you said, but so just to confirm, there's no rate for this stratification. There's no number. There's no like a score that you could give it of no. Okay.
No, not really. I mean, what do you want out of stratification? You want sort of the minimal number of pieces, right? And the algorithm, does generate a stratification which is sort of a local minimum number of pieces, but there might be a different stratification, which has fewer, and you just didn't get to it because of the way you ordered your violators. It almost sounds like a gradient descent sort of question, right? Like depending, this is actually an interesting question. You look at the space of all possible orderings of the violators, and then just run the algorithm based on that ordering, you're going to get to some stratification. Where do you get? Interesting question. Don't know. But with this particular ordering, we know we get a maximal thing, and I think no matter where you start, you'll get to a maximal one, but you can get to different ones.
Any more questions?
Thank you.
So I just have one more comment to make, and that is that together with Primož Krabe and Barbara Di Fabio, which is a colleague of Claudia Landi, we did a lot of thinking about this sub-level set problem, and we didn't get a final result either. So I'm really, really looking forward to your result when you get there. So,
Sublevels, what, in the stratified case, or just?
yes, so the stratified case. We were thinking a lot about that. Actually, spent quite a lot of time drawing pictures and making little arrows on stratified spaces, but
Okay.
nothing that we could say this is a really good result in the end. So I'm looking forward to your.
I mean, I think this is where we are too, though, Neja, I have to say. Like, I don't really know what the good result's going to be. So.
A lot of really interesting questions appeared. So this was some time ago, so I don't really have the details anymore, but it was really, really cool doing it. So I wish you really good luck in drawing your pictures.
Thanks.
So do we have any more questions, please? Well, in that case, I'd really say thanks again, Kevin. This was a very, very nice talk. Thank you very much.
Thank you.
And, well, good luck
Thanks.
with your further work here.